And so our last talk will be given by Mike Brown from Caltech. And Mike will talk about ices in the outer solar system and their connection to the protosolar disk.
Okay, so this is going to be, I think, a pretty different talk from the previous ones for a couple of reasons. One is that I think, as a lot of you in this room, I think there was sort of a lot of geochemistry, isotopic stuff in the early stuff. As an astronomer who primarily studies the outer solar system, things Jupiter and beyond, we don't have a chance to really pick up these samples and start to look in gory detail about their isotopics, about their elemental compositions. We really just have the ability to do remote sensing and try to figure out some big picture things. So one of the things I'm going to do is talk about some of the questions that we have when we look at the outer solar system, show some of the ways we're trying to address that, and in particular with some very new data, and then think a little bit about, at the end, what one might do if you could fly yourself to 40 AU, pick up some stuff, and come back. Good luck. So the processes that are going on, particularly I'm talking about ices in the outer solar system, the processes that lead to the ices we see in the outer solar system are incredibly complex. And this is a similar version to one that you saw from Karen. This is from Karen Oberg, a nice review. And you can't just say, here's a disk, here's a temperature, here's an ice that condenses, or here's an ice that comes in from the interstellar medium, boom, we're done, because there's active gas flowing inward, gas flowing outward, grains, both evaporating and condensing, different snow lines. We hear a lot about the water snow line because most people are talking about the inner part of the solar system, but there are other snow lines further out, and all of these processes contribute to everything going on out there, but in particular to the ices that I'm going to worry about. The observations that I'm going to talk about are most relevant to some of these processes. I'm not going to answer any of the questions about these processes, but at least we're going to talk about how we can use some of these observations to come in. We're going to look at ices on bodies in the outer solar system and talk about things like snow lines, sublimation, differences between gas phase chemistry and grain surface chemistry, very important one, infall of cloud material out here, and also outward spreading of gas. All these things, we at least have a lever to talk about those by looking at these things in the outer solar system. And these things in the outer solar system, let me show you dynamically which are the ones I'm talking about. I'm talking about the things out beyond the orbit of the planets, beyond Neptune, in the Kuiper belt, the trans-Neptunian region. And the most useful way, I think, to look at these is this plot of semi-major axis versus eccentricity. Giant planets, Jupiter, Saturn, Uranus, Neptune, they should all be down here with 0 eccentricity, close enough. But it looks better to put them on top of so I put them there. Each of these little dots is an object, is something in the Kuiper belt or inside the Kuiper belt, somewhere in the range of 20 to 50 kilometers, up to the largest ones are in the couple of 1,000-kilometer range. And you can learn a lot of what happened in the outer part of the solar system just by looking at this plot. The first thing that you see very strongly is this tail of objects going out through here, and I have nicely drawn in this one line. This line is a line of all the objects above this line come to perihelion, their closest approach to the sun. Their perihelion is inside the orbit of Neptune. If they're below this line, they never cross the orbit of Neptune. Crossing the orbit of Neptune sounds like a bad idea. Many of these objects that cross the orbit of Neptune are unstable on the sort of 100 million year timescale, and they're things that are actually, in some ways, they're often closer. They can come in as close as inside of 10 AU. They're easier to study, but they're not quite the frozen remnants that are in the outer solar system. They're more like things that have been in the freezer for 4.5 billion years, and then somebody sat them on the counter for a while, and they're starting to melt. But these things that are underneath here have, for the most part, been beyond the giant planets for all this time. There's some of these objects, we'll talk about some of these that stick up through here in just a minute. So let's zoom in on that area in there. This is the main part of the Kuiper belt. This is called the classical Kuiper belt. Classical meaning what people thought might exist before we saw anything. So these are, in particular, these ones on very low eccentricity orbits beyond Neptune here. And then there are things like these weird fingers that stick up that you can see everywhere. These are objects that are in resonance with Neptune. In particular, these are objects in a 3-to-2 resonance. Neptune goes around 3 times around the sun. These objects go around precisely 2 times, and they're protected from ever having close encounters. Pluto is one of these. It goes inside the orbit of Neptune, but it's actually very stable because it's in this protected resonance. These protected resonance, these scattered objects we see here, and even the existence of these classical objects are all a consequence of the dynamical evolution of the solar system. At some point, early on, the planets were all much more compact configuration. Things might have happened before that, but imagine this compact configuration where Jupiter is pretty close to where it is now, but the other planets are much closer in. As many objects from the outer solar system started scattering around, actually I have a graphic of this, as the objects in the outer solar system started scattering around, it led to instabilities, chaos. These planets got shoved further outward. Jupiter moved inward just a little bit, Saturn moved outward a little bit. And this process led to captures of things in resonances, these big scattering events that led to all those things that have orbits that are similar to Neptune. And what the hard part about this is if you want to read the record of the outer solar system, of these icy bodies in the outer solar system, you really wish they had never moved. It sure would be a lot easier if you could just say, this is where they started, this has this composition, I know where this ice line is, I know what processing this happened, but it's just not true. If there were these objects initially, and maybe there are all these multiple ice lines with these different colored objects that I have now, as this chaos happens, the ones that are closest in to Neptune, as Neptune starts to plow out, they get scattered around the most. They even become part of the Jupiter Trojan population, maybe the Neptune Trojan population. They get scattered all the way out here to those scattered disk in that big eccentric tail that we saw. These other ones go all over the place. There is one little population that kind of doesn't move very much at all. And trying to understand where the objects that you're looking at came from and what it means for the implications for the outer solar system is one of the big games that we try to play. And this big game that we've been trying to play really has been since, God, it was started sort of in the year maybe about 2000, maybe like 1998, when we first started getting good, I'll show you some and then I'll say good and you can all laugh, good spectra of these objects in the outer solar system. It was really the advent of big telescopes like the Keck telescope, where we could look at these very faint objects and start to get a hint of what they're made out of. And I spent a decade of my life and more nights than I care to count staying up all night at using this Keck telescope to collect spectra of these objects. And it was really exciting because we would get a whole collection of spectra and they would look like this. And these we considered really good. And you can laugh now because they're terrible. When I look, I actually was putting this talk together yesterday, and this is from like 2012, and I forgot how bad they were. They really are quite bad. But we see a couple of things. And one is, so first off, we only get to see between about 1.4 and 2.4 microns. Beyond 2.4 microns, the Earth's atmosphere absorbs too much water, and then as you get further out, they're so faint, you just have no chance. If you're seeing anything, even in the middle, there's a gap in the middle where the water in the Earth's atmosphere is a big problem. But you see a couple of things. You see, in general, you see some patterns that look kind of like this, a little dip here, a dip here, a dip here, a dip here, and you see it repeatedly. This is the signature of water ice on the surface of these objects. And it's not everywhere. Here you see ones that really have no hint of any kind of water ice. Sometimes they have water ice, sometimes not. Super exciting. We would go to the telescope, we'd spend hours and we would go reduce the data and be like, oh man, look, it's got water ice on it. That's as good as it gets, man, trust me. So what did we learn via this? Well, you can't really discern too much, but we learned a couple things, like the amount of water ice exposed on the surface of these objects really is a strong function of the size. Astronomers are weird, so small numbers mean big, big numbers mean small, and the largest objects like Pluto's moon Charon, a couple of these larger of the Kuiper Belt objects, had good exposures of water ice. You came down here, but for the most part down here, there were, some of them had a lot, or some of them had some didn't. The red versus the black is the smaller objects are those ones that cross the orbit of Neptune that are much closer in. they were so small we couldn't see them unless we looked at them closer in. So we were never quite sure if it was just because they were close or if they were the same objects as these, but there was a little bit of water here and there. And then the most exciting thing is occasionally we would find an object like this. This is the object Pholus. And early on, there were indications that this is the data. Here's that double dip of water ice, and there's an extra line right there. And that extra little bit, the hypothesis at the time was that it's this spectrum right here due to methanol ice on the surface. And for something like 20 years of studying the Kuiper Belt, that was kind of it. You know, the methanol was really exciting. We could have all these. We had 4 entire methanol detections, and there was some correlation between methanol and the color. This is red objects are over here, less red objects were over here, and it seemed like we were doing a lot of really interesting stuff at the time until yesterday when I was putting this talk together. I was like, man, we spent a lot of time getting a lot of really crummy spectra and making not very interesting plots, but we were doing it, man. So the big change in this field happened a couple years ago with the launch of JWST. JWST, everybody sees all the beautiful images from JWST, fantastic, who cares about images? It's the spectra that are really where it's at, and the spectra are astounding. And I can demonstrate how astounding they are by what I do. If you were to walk in my office and ask me what I'm working on these days, I have a stack of spectra sitting on my printed out because it's fun to put them on the floor and try to arrange them. And people who have never looked at a spectrum before in their life, I can explain by showing a plot that looks sort of like this. I'll use my hands to do it there. I show, here are some spectra now, not with hours and hours on the Keck telescope. Each one of these is, I don't know, probably an hour on JWST. And here's, remember, on Keck we went from 1.4 to about 2.4 microns. And here's what you would see with JWST. What is this one? Anybody remember? Water ice, pretty exciting. How about this one? There's that methanol, yeah. How about this one? Yeah, if you stare at them long enough, you become a true believer. Like I see water ice right there, maybe. And that's, and then we move on, get a lot of these. And so I just want to show you, even if you don't know anything about spectroscopy, it's just sort of blew my mind the first couple ones we see. They look like this. There's a lot more information as you go to these longer wavelengths. Not only is there a lot more information, even this part, the signal noise is so much better than what we used to get. But here's the water ice one. Suddenly you have this huge 3 micron water ice absorption. We'll go through and talk about all the different features on all these different things. But you can see, first off, there's big difference. This black one, you have these features here. This green one, which looked like, okay, there was water ice, maybe it's just water ice, but not as much of it, is utterly different. It's got crazy stuff going on here. We'll talk about the crazy stuff. The red one, methanol, wow, totally different. It's not just water ice plus a little bit of methanol. There are tremendous differences in these objects in the outer part of the solar system that were utterly hidden for most of the past 20 years. Probably the most interesting single result from all of this, and this is from something like a collection of 76 spectra of objects that have been taken over maybe a dozen different programs in the first and second years of JWST, is that these 3 that I'm showing you are just representative. That's kind of it. That's the 3 types of objects in the Kuiper Belt. I would absolutely not have predicted that. I would have predicted that there were more and less water ice, like we saw in that one plot that I had with size, that sometimes you add in a little methanol and it looks like a little bit of water ice with methanol, maybe some stuff where there's not really anything going on, but and that there would be just mixtures between all these, and it really doesn't seem to be true. Let me show you what these look like in detail. Here's the water ice one. You see what we saw before, the double dip here. Actually, you even see that little 1.65 micron is due to crystalline water ice, specifically, not amorphous ice. You have the big 3 micron OH, but the fact that it has this peak in the middle, that peak in the middle is a Fresnel reflection peak of water ice on the surface. It's not just some sort of hydrated something or another. It's literally water ice. A water ice spectrum does this very nicely. It comes back down very nicely. Then, ooh, look at that. That is carbon dioxide, 4.26 microns. And you see a little bit, this is actually an average of all of them, and the average weirdly smooths it out. You see a little bit right there of another line. We'll see it in more detail in a minute. The water ice looks like water ice. Carbon dioxide is there. Carbon dioxide is there in nearly every object we look at, even in places where the objects are closer in the solar system, where carbon dioxide is not stable. So it's clearly trapped in some other material that's more stable. Very difficult to figure out what it's trapped in. We actually have an interesting program looking at all the satellites of Saturn, where they all have trapped CO2 too, trying to disentangle all the different sources. But we're still trying to figure that one out. So that's I'll call that a water ice one. The second one that we saw was methanol. There's methanol right there. There's the line that we could see from the ground. At the doublet is the telltale sign of methanol. Huge absorption here. No Fresnel peak. So this is not water ice. This is some sort of OH stretch feature, probably some organic thing. I say probably some organic thing because the OH stretch, if you remember, the water went smoothly up here like this and back down again. All of this little part that's been chomped out through here is due to some sort of organics. This is all the CH stretch in aromatic and aliphatic hydrocarbons in through here, and we actually need higher resolution to really disentangle what all these things are in through here. I talked about carbon dioxide. There's the huge carbon dioxide line. This peak is also due to carbon dioxide. Come back to that at the next one. And that little divot right there is actually 13 CO2, so you have a carbon dioxide, carbon isotope there. Here's the CO line I talked about before. This one, I'm still trying to decide if I believe that this is something or not. And then there's some carbon dioxide and some other stuff in through there. Very different, hugely different spectrum than the one before. And so finally, let me show you the one hugely different spectrum again, which is insane. First off, I think a little water ice. You see the 1.5 and 2 micron lines. Yeah, maybe even a little methanol in through there. These two lines are both carbon dioxide. They're combination bands of carbon dioxide. They are incredibly weak combination bands of carbon dioxide, so the fact that you see them means there's a ton of carbon dioxide. Some sort of OH thing, organics like we saw before. Big dip, the big dip, this going up, this going back down, little doublet, going up, going down, there's the 13 CO2 again. All of this stuff in here, and that is all due to a very weird specific form of CO2. So when people first saw this spectrum, everybody was pretty confused as to what possibly could cause these things that look like emission lines. Is it gas emission? Is it something else? It's not. It's tiny little 1 micron grains of CO2 sitting on the surface of these objects. And it can't be a thick layer of tiny layers, of tiny things, because a thick layer would bring this part of the spectrum down to 0 because there's so much absorption in through here. It is really strange, and so far there are no plausible explanations for why you said there's so many objects that are so similar that if you have 3 micron grains, it doesn't look like this. If you have 0.5 micron grains, it doesn't look like this. There are 20 objects that look like this, all with kind of 1 or 2 micron grains in a very thin layer sitting on the surface. Unclear what's going on. But we can now take all these objects, because they're now basically these 3 types of objects, and we can look at where they occur in the solar system and see what we can learn. So here's that plot again of semi-major axis versus eccentricity. The blue ones are water. The red ones are methanol, and the green ones are the ones with all the CO2. The blue ones are a little bluer. The red ones are a little redder, and I don't know why I chose green, because that's the other color that I had. And, you know, I already told you before, expect to see nothing. It's not quite as bad as seeing nothing. I mean, one of the things you'd really like to do is, first off, there are huge differences. These huge differences were caused by something. Those processes that I showed you at the beginning are probably the processes that do it. Snow lines, maybe, that there are, water ice ones, and then the water ice ones have very little of organics or some of the other materials in there. Is there something going on that we can somehow disentangle? And the answer is a little bit. And the way to do it is to remember back when I showed the plot, which I'm going to show again, that the things that are closest get scattered the most, and they become Jupiter Trojans, they become Neptune Trojans. Some of the other things become Neptune Trojans too, but that's where they go, and they get scattered out to the very distant part of the scattered disk. And what that's telling you is if you look carefully, these things that are scattered out the most, the numbers are small, but there you see blue ones. You see blue ones coming in. You see some of the red ones, the methanol ones too. There's another kind of set of programs that I haven't put on here that looks at this region more, that finds increasingly more of the water ones. It really looks like the centaurs, these objects that are coming in closest, are kind of the water ones. And the most scattered objects are kind of the watered ones. And what I think is really interesting is if you look at things like the Neptune Trojans, there's a program that's looked at the Neptune Trojans. Most of them are the water ones, not exclusive. There are a couple of the sort of methanol-like ones. And one of my favorite ones is if you look at things coming in from the Oort cloud. Well, we don't have too many spectra of that, but here's one. This is comet Bernardinelli-Bernstein. We'll call it BB. Here's the BB. It's right now at about 20 AU. It's coming in from the Oort cloud for the first time. It looks exactly like these water ice things. They're nice little Fresnel peak. The only difference here, this is actual CO2 emission. It's evaporating as it comes in. There's CO emission coming in through here. And so this is one of the things, the points that I want to make, is that a lot of this stuff that we have coming in, the centaurs that become Jupiter family comets, the things from the Oort cloud, I think they're all from a specific part of the outer disk. And we often think of them as representative of, here's the materials in the outer solar system. I think the answer is that's not true. In fact, we talk about it for things like the Jupiter Trojans, the Lucy mission that's on its way to visit the Jupiter Trojans. And one of the reasons for proposing it and selecting it is like it's a chance to go see parts of the outer solar system. And I think we're seeing this part of the outer solar system. I think when we get there, we are still not going to have much of an idea for what these much more distant parts of the outer solar system are. So I have just a little time left, so I want to say a couple things. Do I want to talk? Well, I wanted to talk a little bit about methanol. The methanol objects are weird, and I don't really know exactly what they're telling us about, if it's some kind of snow line or if it's methanol coming in. There are nice models that try to tell you where methanol comes into a planetary system, and they come in through different methods. And the real take-home message from this chemistry and trying to understand these ices sort of theoretically, modeling them, is that it is awfully complicated because you have pristine ices that can come in and stick around. You have ices that can come in and be released from grains, but then reaccumulate. You have chemistry that will happen. It is a lot more complicated, I think, than just thinking about like maybe part of the inner solar system where it's hot and everything recondenses and life is a happy place. Okay, so I'm going to very quickly talk a little bit. I can do it quickly because Karen spent a lot of time on this one, so I'm not going to spend nearly as much with just talking about deuterium. And I want to talk about deuterium specifically deuterated water, and specifically in the sense of infall of cloud material, because I'm less concerned about what's going on the Earth, but in the outer part of the solar system, the difference between infalling cloud material that pristinely makes its way into the outer solar system versus stuff that comes in as H2 gas and then combines and makes water as it works its way out in the outer solar system. The deuterium ratio between those two reservoirs is massive. So we don't have to sit around and talk about parts per mil or parts per something. We talk about parts per part, which is good for astronomers because we can't measure things all that precisely. But if you give me a factor of a couple, like a D to H ratio that's terrestrial versus 2 to 5 to 10 times elevated, like I can measure that. So, and there are, Karen showed some models. As you start to look at D to H models in the outer solar system, you'll find you can almost come up with any answer you want. But here's one that includes some time variation, starts out all the same, and then material falls in from the cloud with higher D to H ratio. That's where it's falling in here like this, and it kind of spreads out. And so you can come up with models like this, but what you really want are data to constrain you, not just from comets, which I think are a very specific reservoir, but you actually want them from across the solar system. And it was an interesting paper a couple years ago from Roger Clark that basically, there are a lot more comments that he could have put on here, but he claimed to be able to measure the D to H ratio in the icy satellites of Saturn. And I'll show you the data in a minute. And I have to say, every spectroscopist I know is utterly dubious about this, and I'll show you why. You'll be dubious too. Here's why to be dubious. Here's the spectrum of the B ring of Saturn. Water ice, huge amounts of water ice, more little water ice. There's there we are, the Fresnel peak. There's the line. There's the 4.13 micron DH stretch fundamental, analogous to the OH stretch that's over here. Do you see it? It's right there. Oh yeah, wait, there it is. It's right there. That little wiggle. He measured the little wiggle on the B ring of Saturn and on these other satellites and made this story. And if I were a betting person, I would say absolutely wrong. And the answer is he was absolutely right. So here's now JWST data. There's the 4.13 micron line. This is the ring. As I told you, we have this program looking at the Saturnian satellites for the CO2. The 4.13 micron line is everywhere. He was absolutely right. You can measure in the solid state in these objects these lines, and the numbers are not. I don't think they're quite right. He didn't do a very. It was more concentrating on measuring the thing than on calibrating. So we're doing some calibrations in the lab right now, but these numbers are going to come in something like this, maybe a little bit elevated, maybe like twice terrestrial. Phoebe, that's not true, so you can ignore that point. But these seem to be right, and it's an interesting idea that we can now start to use these to understand interstellar ice inheritance from the entire solar system. So I'm supposed to talk about sample return. I don't know anything about sample return. I'm an astronomer. We don't do sample return. We return photons. Those are better than samples. But if I could do sample return, there are interesting things that you would want to do. Like, at this point, we really don't just need to go and get a grain and get like some weird little isotope of elements that nobody's ever heard of. We really would love to just get some bulk ice compositions, like trying to understand how the outer part of the solar system put itself together, the effect of ice lines, the effect of chemistry there. These bulk ice compositions would be tremendously valuable. There is really interesting isotopic information available too. I talked about water because it's the easy one for us to do, but you can imagine you're doing a sample return. You don't actually need to do the ones that are parts per part. You can actually do these measurements where you're trying to look at this inheritance of interstellar ice and the difference between ices that condensed at 10K in a cloud and their isotopic ratios and their isotopic positions compared to some kind of chemistry that happens in a much warmer interstellar protoplanetary disk. So, and I just want to end on how to get there, get the material, and get back. And the answer is I have no idea. Like, that seems crazy to me, but here we are talking about it. So I think it's at least worth thinking about what you would actually do. And generally, people don't talk about and think about what you would do for this part of the solar system because we all think it's impossible. So it's time to start thinking about it.